Hello viewers, welcome to Add-on. In this question, we are gonna explain the input and the output characteristics of the common base transistor, which is a CB mode transistor. So at first, let us draw the circuit diagram for a CB mode. So for a CB mode, as we know, as the name suggests, it is the common base mode. So what happens in the common base mode? The base terminal of the transistor is connected to the ground. Transistor has three terminals. This terminal is the emitter terminal, this is the collector terminal, and this is the base terminal. So this base terminal is connected to a ground. Okay. So this is the main principle of a CB mode transistor. So at first, let us draw the circuit diagram of a CB mode transistor. Okay. Okay. So this is the circuit diagram of a CB mode transistor. So what happens in the CB mode transistor? The base terminal is taken as common for the both input and the output, or the base terminal is connected to the ground. This point is connected to a ground. Okay. And this point is common for both the input portion and both for the output portion. This is the principle of the common mode, this common base mode transistor. And the input is applied between the emitter and the base terminal. We can see that the input, this is the input, this is applied between the emitter terminal and the base terminal. Okay. This is the emitter terminal E, this is the base terminal B, and this is the collector terminal C. So the input is applied between the emitter terminal and the base terminal, and the output is taken between the collector terminal and the base terminal. We can see from here we are getting the output, so it is between the collector terminal and the base terminal, and here we are applying the input, so it is between the emitter terminal and the base terminal. Okay, so what happens here is that this is the, we can say this is the NPN transistor configuration of CB mode. Okay, so the input is given between the emitter and the base terminal, and the output is taken from the collector and the base terminal. The input voltage is denoted by V of BE, or the voltage between base and emitter. The input voltage is denoted by V of BE, which is the voltage between the base and emitter, and the output voltage is denoted by V of CE, which is the voltage between the collector and emitter. Okay, this is the input voltage and this is the output voltage. Okay, so in all the configuration, the V of B, this junction, this base emitter junction, this junction is always forward biased. This is the main, we can say, configuration for the transistor operation. And this V of C, or collector emitter junction, or we can say this V of C, it is the output voltage, but the base emitter junction is forward biased, and the collector base junction, which is the CB junction, this is reverse biased. So this is the configuration of a transistor. Okay, the base emitter junction, because as we know, the transistor, for a NPN transistor, these two N and P form a PN junction. This is the base emitter junction, and these two N and P form a PN junction. This is the collector base junction. So in order to work properly, the transistor must have its base emitter junction forward biased and a collector base junction reverse biased. Okay, so the emitter base terminals are mainly forward biased because let us work here. The emitter terminal, this is highly doped. Okay, I am denoting by the plus symbol. The base terminal, this is very lowly doped, and the collector terminal is moderately doped. Okay, so the emitter terminal is N-type, the base terminal is P-type, and the collector terminal is N-type. So the emitter terminal consists of a lot of number of electrons. So when the base emitter junction is forward biased, as we know, when the PN junction is forward biased, the potential barrier between them decreases. So as the potential barrier decreases, the electrons from the emitter will enters into the base, and the holes from the base into the electron. Okay. So the free electrons from the emitter move to the base, and within the base, as we know, the base is lightly doped. So the base consists of very few number of holes. So if we say total number of 100 electrons move from emitter to base, only 5 number of electrons will recombine with the holes of base, and the rest 95 electrons will passed on to the collector. Okay. So this 5% or 5 number of electrons which are recombining with the holes in the base terminal forms the base current. Okay. So as we can see, this is very small fraction of current. So the value of base current is typically very small. Okay. And this emitter current is responsible for the flow of base current as well as collector current. Okay. Because this base current, as we can see, if 100 electrons are moving, 5 are responsible for the base current and 95 are responsible for the collector current. So emitter current is equals to base current plus collector current. Okay. So now we are going to describe the input-output characteristics of the common base configuration. So at first, let us discuss about the input characteristics of common base configuration. Okay. So the input characteristic is basically the relationship between the input current and the input voltage with constant output voltage at the parameter. So as we can see in this figure, the input current is what? The input current is I of E. Okay. This is the input current against the input voltage. As I have said here, this is the input voltage V of B, and with the output voltage as a parameter. So this V of C is the output voltage. So this is the parameter. Okay. So if we construct the curve will be somewhat like this. The curve will be somewhat like this. So this y-axis is the IE, emitter current, which has a unit of milliampere, and this x-axis is the input voltage, which has a unit of volt, and this is the characteristic curve like this. So suppose here the value of V of CB is equal to 20 volt. Okay. So as we have said, the collector base terminal, this terminal is always what? This terminal is always reverse biased. Okay. So this is the input current, this is the input voltage, and this is the output voltage, which is a parameter which is used for defining the curves. Okay. So in the common base configuration, the curve is plotted between IE and VB, keeping V of CB as a constant. Okay. So the V of B, this V of B is increased initially, keeping the V of CB constant. Okay. This V of B is increased, keeping the V of CB constant initially at 0, and the value of current IE is noted. Okay. Then similarly, the value of V of CB is increased and kept constant, and VB is increased and the input current IE is noted. Okay. Because the input side is V of B, the base emitter junction. This is the input side. So this junction is forward bias. So the input resistance is very small because a lot of electrons are flowing from emitter to the base. So a lot of current is flowing from emitter to the base. So as the current flowing is large, the resistance will be very low. Okay, in the VB. So there is a rapid increase in the emitter current. We can see that here, as we are increasing the base emitter voltage, which is forward bias, as we are increasing the base emitter voltage, the emitter current is rapidly increasing. Okay. And we have said that the output voltage, which is V of CB, this is what? This is reverse biased. Okay. So If we increase the reverse bias, the width of the depletion region, what happens? As the voltage VCB, which is the reverse bias voltage, as it is increased, the width of the depletion layer between the emitter base decreases and the cut-in voltage is reduced. So the curve, what happens? So the curve will drift to the left hand side. Okay. So if we, this is the value, this is the curve which is defined at VCB at 20 volt. Next, if we draw another, this will be the curve, and let us draw another. This will be the curve. This will be the curve. The last curve is for 0 volt. Next curve is what? Next curve is for 10 volt. Okay. So this is the curve. As we can see, when the value of VCB is equals to 0 volt, okay, at this particular voltage, we can see at this particular point, the value of VCB at the value of VCB equal to 0 volt, the value of current is minimum. And as the voltage is increased, the value of current is increasing, and at the value of 20 volt, the value of current. So why does it happens? This happens because, as I have said, the the VB junction is already forward bias. So if we increase the value of VB, the current will also increase. Okay. But the VCB, this is the output voltage. So if the value of VCB increased, okay, the width of the depletion region between the emitter base junction will gradually decrease. So the cut-in voltage will drift to the left hand side, this side. Okay. Because VCB is the reverse bias voltage between the collector and the base terminal. So as the reverse bias voltage is increased, the depletion region between the collector and base will increase, but the depletion region between the base and emitter will decrease. Okay. So the curves will drift to the left hand side. So if we increase the value of VCB, the current will gradually increase. Okay. So this is for the input characteristics. Next up, I am defining the output characteristics in the right hand side. So the output characteristics is the relationship between the output current. Here we can see the output current is IC against the output voltage, which is V of CB. Okay, this is V of CB. Okay, this is V of CB. This is the output voltage, and we keep input current, which is IE, as a parameter in this case. So in the input characteristics, the plot was between input current and input voltage, keeping the output voltage as a parameter. Okay, but in the output characteristics, the output current and the output voltage are plotted with the input current as a parameter. Okay, this is V of CB. This is V of CB, which is the output voltage, because this is a collector and base terminal. So the voltage between it is V of CB, and the voltage between it is V of BE. Okay, input voltage and output voltage. So let us draw the output characteristics. Output characteristics will be like this. This x-axis, this y-axis will be output current, which is collector current in the range of milliamperes. This x-axis will be output voltage, which will be V of CB volt, and the parameters which we have keeping constant here is the input current. The input current is emitter current. So this is the value at emitter current is equal to 2 milliampere. This is at I is equal to 3 milliamperes, and this is at I is equal to 4 milliampere. Okay. So this region of the curves, this particular region of the curve where the value of IC is 0, this is the cutoff region. Okay. This is the active region, and this particular region is the saturation region. Okay. So when the input current IE is equals to 0 milliamperes, then it is the cutoff region. Okay. And in the saturation region, as we all know, the emitter base junction as well as the collector base junction both are forward biased. Okay. The emitter base junction and the collector base junction both are forward biased. This is this region. And in the active region, what happens? Emitter base junction is forward biased, which collector base junction is reverse biased. Okay. So this region is the active region. In the active region, the value of IE is gradually increased. We can see from 2 milliampere to 3 milliampere to 4 milliampere. And the output voltage, okay, the value of IE is gradually increased and it is kept constant. And the output voltage V of CV is increased further. And the output current almost remain constant at this point. Okay. So in the active region, the curve is almost flat. The output voltage only causes a little change in the output current. Okay. So why this saturation, you can say why this curves become constant. So this IE, this is the emitter current, right? So we know this emitter current is responsible for the base current as well as the collector current. Okay. So this collector base junction is what? As I have said earlier, this collector base junction is reverse biased. So if we reverse bias the collector base junction, then the depletion region between the collector and the base terminal increases. So if the depletion region between the collector and the base terminal is increased, the electron can't pass through the base to collector terminal. Okay. So we can see at a particular value of VCV, the current are no longer increasing. The value of current has become constant because no electrons can pass through the base terminal to the collector terminal no more. So the value of the collector current IC has become constant. Okay. And as this value of IE is increased, the value of IC is gradually increasing because here we can see this IE is responsible for the collector current. Okay. So if the value of IE is increased, it is natural the value of collector current will also increase. So as the value of I is increased, the value of collector current will also increase. But at this particular point, when the value of VCB or the reverse bias voltage reaches this particular value, no more electron will flow from the base to collector. So the current at that point become constant. So we will get a constant curve at that point. So this is for the input and output characteristic of CMOS transistor. Thank you.